Welcome to the lecture titled Online Identification of TITO Systems. In our last lecture, we have studied the offline identification of TITO systems. In this lecture, we shall see how simple online identification scheme can be applied for TITO or two input, two output systems. What we have described in our last lecture is that given a TITO system which has got two inputs U1 and U2 and two outputs Y1 and Y2, we can add a modified relay of the form a relay with one controller Cn1 and a gain in parallel K1, and similarly a controller Cn2, a relay and again in parallel with the relay K2 can be added. These modified relays can be put in closed loop with negative feedback with of course the set values R1 and R2. So, this is how we get an offline identification scheme, where the relay is switched on or modified relay is on during identification, whereas it is switched off. The modified relay is off during normal operation of the decentralized control system, normal operation. So, how it is different from an online identification scheme, that we shall see. Given a TITO system, again this is your TITO system which has got two outputs Y1 and Y2 and corresponding inputs U1 and U2. I can add relay of course in parallel with a controller. So, we will have controllers in parallel with the relay. And then put the relay in closed loop in this form. So, similarly, for the second loop, we will have the negative feedback in this form. And of course, now we can have the set values R1 and R2 or S1 and S2 as we have used in our last lecture, S1 and S2. These are the reference inputs or set point inputs. Okay. So, how this is accomplished, how this online identification now is done, online identification. In the online identification, relay will be on during identification and off during normal operation. Now, when relay is off during normal operation, what happens? The TITO system will be subjected to decentralized control, whereas in the earlier case, when the relay is on, the controllers are to be switched off. So, basically not only the relay, the controllers are also to be switched off. So, controllers Here, unlike the online identification case, in offline identification scheme, the controllers remain off during the identification, which is not so in online identification scheme. I mean to say, the controllers are always there in the loop. That means, when decentralized control is effected, that time relay is switched off, otherwise relay is switched on for identification of parameters of parametric models of the TITO system. So, these are the basic difference between the two, and not only we are getting a simple scheme, simple online scheme, the added advantage of this one, that if the TITO system is subjected to some load inputs, some static load disturbances like load inputs, then the output is not getting affected by the presence of controllers in the loop during identification. There is the major advantage we get with the online identification scheme, and unlike offline identification scheme, the controller need not be switched off during identification. So, this is the fundamental difference we have between the offline identification and online identification schemes. Now, I shall go to the online identification scheme, which can be given in this form. Now, in this structure, as you see, the L1 and L2 represents the static load disturbances, and M1 and M2 also represents the measurement noise. So, we have got a controller connected in parallel with the relays throughout the operation of the system and during the relay experiment as well. So, that is the basic difference we have between the offline identification scheme and the online identification scheme. So, what are the major benefits one get from this arrangement, this online identification scheme? First is how you have to do. The relay is permanently connected in parallel with a controller, and the controller is assumed to have integral action. So, what type of controller we have to use? Either PI or PID or IE controller. Now, what is the benefit you get by that? Then the effects of static load disturbances are cancelled, and we obtain symmetrical limit cycle output for symmetrical relays. If the controller is disconnected, as you can see from here, suppose I disconnect the controller during the relay experiment, what will happen? The static load disturbance will influence the input to the TITO process. That means, whatever signal you are getting, whatever rectangular pulses you are getting, that will get added by the static load disturbance, and ultimately you will get asymmetrical input to the system. Now, asymmetrical or shifted version of the input signal to the system. So, you will get an input of this form, and corresponding to this asymmetrical input, the output will become asymmetrical. So, that will not happen provided we have a controller during the relay experiment. So, that is the major benefit we get from the scheme. Now, further we can get a simpler equivalent representation, equivalent block diagram representation for the online scheme compared to that of the offline scheme. A simpler one can be obtained. How it will look like? Then the equivalent representation of the block diagram for online identification scheme looks like this, where the relay is basically a TITO system. Sorry, this will cover like this. So, the relay will experience an inner feedback controller the TITO system is subjected to inner feedback controllers. So, that is the beauty of this scheme. When the online identification scheme is given or shown in equivalent form, then it is apparent from this figure that the relay is basically the TITO dynamics subjected to two inner feedback controllers. And what is the benefit of this putting inner feedback controllers? That the TITO dynamics can get modified, or the open loop TITO dynamics can be modified with the help of the two inner feedback controllers GCL1S and GCL2S, and thus we can relocate the poles of the open loop TITO dynamics to suitable positions. Thus, the relay feedback will result in not only symmetrical output, rather it can result in symmetrical output for difficult TITO processes as well. So, that is the major benefit one gets from the online identification structure we have provided. Now, also I can get the relation between the output to the static load disturbances in the form of y1 upon L1 is equal to G1 upon 1 plus G1 G CL1 upon 1 plus N G1 upon 1 plus G1 G CL1. What I mean by that? Let us find the transfer function between y1 to L1. Then assuming R1 to be 0 that time, R2 to be 0 that time, for the upper case, when the TITO process or dynamics is assumed to have decoupled dynamics, that time the transfer function between the output to that of the static load disturbance can be given in this form. Upon simplification, which gives us in the form of G1 upon 1 plus N G1 plus G1 G CL1. This is for one loop. Similarly, I can find the transfer function of y2 upon L2 to be of the form G2 1 plus N G2. In this case, this will be N1, this will be N2, N2 G2 plus G2 G CL2. So, what are G1 and G2 here? G1 and G2 are the equivalent representation of the dynamics of TITO system, of the dynamics of the TITO system, when it is assumed that the TITO system is decoupled. So, when the TITO system is decoupled, obviously we get the equivalent representation of the whole TITO system dynamics in the form of G1 and G2. That means, as if we have got two single input single output systems of the form G1S and G2S. Corresponding to that, the transfer function between the output and load disturbances can be expressed in this form. So, why I am expressing this? The reason is that if you find the steady state values of the output corresponding to the load inputs or static load disturbances, limit S tends to 0, y1 upon L1 S will give you 0 when the GCL1 or GCL2 or the controllers have integral action or integrators. When the controllers have integrators, basically one s will appear in the numerator. So, ultimately it will be s times your G 2 upon 1 plus N 2 G 2 plus G 2 G C L 2 dash. It will be available in this form. When s tends to 0, whole term becomes 0, and that is how the effects of the load disturbances L 1 and L 2 are nullified in the output of the system. So, the limit cycle experiment or the relay feedback experiment will not be disturbed by the presence of static load disturbances. Okay. So, this is the major benefit you get from the online identification scheme. Now, I will describe the dynamics of the TITO system by the model transfer matrix. Now, the TITO system will be identified by or will be represented by two single input, single output, second order plus time delay transfer function models. Okay. So, the TITO system will be represented by two single input, single output models, transfer function models. Then the model transfer matrix will be GMS is equal to GM1S 0 0 GM2S. So, we can write the model transfer matrix in the diagonal form. Now, what form of GM1 and GM2S will have? One can choose the single input, single output transfer function models to be of the form GMIS is equal to KI e to the power minus DIS upon STI plus 1 square for all I equal to 1 to 2. That means, GM1S will be equal to K1 e to the power minus D1S upon ST1 plus 1 square, and GM2S will now become K2 e to the power minus D2S upon ST2 plus 1 square. So, the TITO system dynamics has got how many unknowns? Means as far as the two single input, single output transfer function models are concerned, number of unknowns will be 1, 2, 3, 4, 5, 6. So, we will have 6 unknowns, those are to be identified or estimated. Okay. What are those K's, D's and T's? K's are the steady state gains. So, we will have two steady state gains K1 and K2. So, K's are the steady state gains. What are the T's? T's are the time constants. So, T1, T2 are the time constants, and what are the D's? D's are the D1 and D2 are the time delays. Please see the changes. Earlier I have used the theta variable for the time delays, but in this study we are introducing D's for the time delays. Okay. So, D1, D2 are the time delays of the transfer function models. Okay. Now, we have assumed a second order transfer function model for the dynamics of for two SISO models of the TITO dynamics. Why we have assumed the second order dynamics? I mean to say GM1 as I have written by K1 e to the power minus D1S upon T1S plus 1 square. Often one can use any sort of transfer function model here. So, G1S can be of the form K1 e to the power minus D1S times divided by T1S plus 1 also. So, we can represent the SISO transfer function model by some first order plus date time model, unlike the second order plus date time model that we have assumed for our study. Okay. Now, can we take any other sort of models? GM1S is equal to say your K1 e to the power minus D1S times T1 T2 S square plus T1 plus T2 S plus 1. Can we take any other form like GM1 is equal to K1 e to the power minus D1 S upon your tau 1 S square plus 4 tau 1 S square plus tau 2 S plus 1. Can I take in this form? That means, this represents the dynamics for an underdamped system, this represents the dynamics for a second order transfer function model with two distinct poles. So, we can no doubt the analysis cannot be or may not be restricted to only the second order plus date time model we have chosen, rather we can use any sort of model, but there is one limitation. We shall make use of describing function in our analysis. So, when you make use of describing function in your analysis, the describing function does not result in more analytical expressions, only the phase and magnitudes of describing functions or the analytical expressions involving describing function can be considered. In that case, number of unknowns, the number of unknowns that can be identified will be limited. So, since we are using describing function and the describing function does not give more analytical expressions, we are forced to choose simple transfer function model that has got less number of unknowns. So, if I look at the transfer function models, number of unknowns we have in the second order plus date time model, this second order plus date time model are 3. So, we have got 3 unknowns here. Similarly, the second one we have got 3 unknowns. You have got 1, 2, 3, 4, 4 unknowns, and 1, 2, 3, 4. So, you have got 4 unknowns. Now, since the last two transfer function models are having more number of unknowns, I am not using those in our analysis. Coming to the first two, now the first order plus date time model has got 3 unknowns, whereas the second order plus date time model of this form has got 3 unknowns. So, why not to use the higher order transfer function model that can replicate the dynamics of many practical systems. Okay. So, that is the benefit we get from this second order plus date time model, and that is why I am going to use this transfer function model in our analysis. Okay. Now, the PID controllers will be given by the series form of PID controller. So, this gives the dynamics of a series PID controller, where you have got beta in the PID controller as beta 1 and beta 2. When I equal to 1 and 2, beta 1 and beta 2 are the derivative filters which are of very small value. So, for practical purposes, for each in analysis of analytical expressions we are going to handle later on, what will be done? Beta 1 and beta 2 will be assumed to be 0. There is no harm, because normally these values are very small percentage of that of the time constants T, D, I dash. Okay. Now, so the controller in the matrix form and that too in diagonal form are given by GCLS is equal to GCL1S 0 0 GCL2S, where GCLIS will be equal to KCI dash times 1 plus 1 upon T I dash S times 1 plus T d I dash S upon 1 plus beta I T d I dash S. Okay. So, we are using series form of PID controllers. Now, let the describing function matrix for the two relays be given by the nonlinear matrix n is equal to n 1 0 0 n 2, where n 1 and n 2 are the gains of the ideal relays for loop 1 and 2. So, how the gains are described? Now, n 1, as you know, n 1 is equal to 4 h 1 upon pi a 1 and n 2 will be equal to 4 h 2 upon pi a 2 for ideal relays. So, when the relay possesses some hysteresis, in that case these expressions are to be modified. Now, what are H 1, H 2, A 1, A 2? H 1, H 2 are the relay settings and A 1, A 2 are the peak amplitudes of the sustained oscillatory outputs. So, thus we get the dynamics of the relay in general form, and I is equal to 4 h I upon pi a I for all I going from 1 to 2. Okay. So, this is how we get the dynamics for n also. Now, we will start with the process or stages or the procedure for estimation of the parameters associated with transfer to SISO transfer function models. First, we will try to identify the steady state gains given by K I for all I equal to 1 to 2. That means, how to find K 1 and K 2 will be described now. Now, measure average values of the process inputs. What are the process inputs? U 1 and U 2. These are the two process inputs, but in first instant or at any instant of time when R 1 and R 2, the two set values are not equal to 0, that time you measure the process inputs and denote that by U 1 1 and U 2 1. When you measure the average values of the process inputs, the average of process inputs, that time denote the average values of the process inputs by U 1 1 average and U 2 1 average. Where are those U 1 1, U 2 1? You see what are the process inputs and output. If you go back to the model, we have got the input U 1 and output Y 1. Similarly, input U 2 and Y 2 the second output. Okay. Now, in variable form you have to write the lower case letters. Okay. U 1 in Laplace transfer form is the upper case, and in variable form or lower case in the signal form it gives you U 1. Similarly, the output is Y 1 and U 2 and Y 2. Okay. So, measure those values, average values when R 1 and R 2 are having some values, okay, and at that time denote the process inputs by U 1 1 average and U 2 1 average. Similarly, the process outputs at that instant are denoted by Y 1 1 average and Y 2 1 average. Now, use some temporal disturbance at the set points or reference inputs to measure the above average values in the second instant, where the process inputs will be when you give some disturbance like change the value of R 1 or R 2 by some small magnitude, then you will have different inputs and output variables or measurements. So, at that time let the process inputs when the temporal disturbance is applied. B, process inputs, B, U1 average 2 and U2 average 2 at the second instant. Okay. Similarly, the process outputs Y1 average 2 and Y2 average 2. So, this is how I obtain how many 1, 2, 3, 4, 5, 6, 7, 8, 8 measurements are obtained. Okay. So, with those measurements it is possible to estimate the steady state gains using the expressions K 1 is equal to xi upon U11 average times U22 average minus U12 average times Y12 average whole of times U11 average U22 average minus U12 average U21 average. Similarly, K2 can be having an expression of this form. So, use the measurements and estimate the steady state gains K1 and K2, where xi is given by this horrible expression. Now, these are very simple to obtain. The procedure for obtaining the expression for steady state gains will be explained now. How do I get those expressions? Now, if limit cycle occurs for some non-zero H1 and H2 and non-zero R1 and R2. So, R1, R2 are not equal to 0, not equal to 0. At that time, make the measurements and take the measurements in Laplace variable form first. Then the outputs Y1 and Y2 at first instance will be denoted by Y11, Y21, and similarly the outputs at the second instant, like when the temporal input is given by Y12 and Y22. When you put that in the matrix form, what you get? Basically, these are nothing but your measurements U1 1, U uppercase, U2 1 0 0 with G1 1, G1 2, G2 1, G2 2. And let me complete this 0 0, and you will have U1 1, U2 1. Similarly, you will have U1 2, U2 2, 0 0 0 0, U1 2, U2 2. Or if you expand this, let me write one simple expression. How do I get Y11? Y11 is nothing but G11 U11 plus G12 U21. So, in the first instant, forget about this first instant, then what you are getting? Y1 is equal to G11 U1 plus G12 U2. Is it so or not? Yes, definitely. If you see the block diagram now, what is your Y1? Y1 will definitely is made up of two components G11 U1 plus G12 U2, G12 UT. So, Y1 is given by this Y1, the signal at this point is given by G11 times U1. So, G11 U1 plus this signal is getting added here. So, G12 and the input is U2 now. So, at that time assume this to be 0, L1 and L2 to be 0 and signal measurements M1 and M2 errors are to be 0. Then you get the expression G1 to U2. So, it is not difficult to get those simpler expressions first, which can ultimately be converted to some matrix form and to some ultimate form given by this. Okay. So, after obtaining this, what I will do? Then if this way we can find the expressions for first instant, put 1 1 at the first instant. Similarly, at different instant of time, second instant, the output y 1 will be y 1 2 will be nothing but u 1 2 or g 1 1 u 1 2 u 1 2 plus g 1 2 u 2 2. Okay. So, we obtained the signal in transfer in Laplace domain in this form, which ultimately can be written as now g 1 1 g 1 2 g 2 1 g 2 2 will be equal to the matrix inversion will get involved. So, which can be solved and found as u 1 1 u 2 2 minus u 1 2 u 2 1 times you will have again your u 2 2 0 minus u 2 1 0, then minus u 1 2 0, then u 1 1 0, then 0 u 2 2 0 minus u 2 1 0 minus u 1 2 0 u 1 1. So, when you find the matrix inversion of this one, because ultimately g 1 1 sorry stop. Oh. Okay. So, when I write this in the form of g 1 1 g 1 2 g 2 1 g 2 2 is equal to, take this to the left hand side. So, you will have inversion now, matrix inversion u 1 1 u 2 1 0 0 0 0 u 1 1 u 2 1, then u 1 2 u 2 2 0 0 0 0 u 1 2 u 2 2 inverse times y 1 1 y 2 1 y 1 2 y 2 2. So, this is how you get. So, I find the matrix inversion which comes out to be of this form times it will be your y 1 1 y 2 1 and y 1 2 y 2 2. Okay. So, this is how you get the expression for G now. Now, when the TITO dynamics, dynamics is represented by two single input single output dynamic model form, assuming that there is decoupling between the two loops, then we know that G 1 can be given in the form of G 1 1 G 2 2 minus G 1 2 G 2 1 divided by G 2 2. Similarly, an expression for G 2 can be written, okay, where in this case what will happen, it will be G 1 1 G 2 2 minus G 1 2 G 2 1 divided by G 1 1. So, these are the two decoupled transfer function representation of the TITO system dynamics. Okay. So, when I consider the upper one, then upon substitution of G 2 2, upon substitution of G 1 1 G 1 2 G 2 1 G 2 2 here in this expression, then I get finally this K expression for K 1 and K 2. How do you get? After obtaining the substitution of this one here, how much you will get? Basically, G 1 will result in U 2 2 Y 1 1 minus U 2 1 Y 2 1 times U 1 1 Y 2 2 minus U 1 2 Y 1 2 minus of U 1 1 Y 2 1 minus U 1 2 Y 1 1 times U 2 2 Y 1 1 minus U 2 1 Y 2 2. What is, when I substitute these G's values G 1 1 G 1 2 G 2 1 G 2 2 in this expression, I get in this form divided by U 1 1 Y 2 2 minus U 1 2 Y 1 2 times U 1 1 Y 2 U 2 2 minus u1 to u2 1. Now, when you take the how we find the steady state gains? Now, when I take the average value of this one, when I take the average value of this one, then I get the k. What is that k 1? K 1 is now average value of output of G 1 upon average value of input of G 1. So, basically what has happened? I have got a G 1 dynamic suppose, and the outputs input is now u and output is y. So, when I take the average, that means y avg upon u, sorry, this will be the small letter now, because I am measuring the signal and finding the signal's average value, then u avg will give you the steady state value or DC value, okay, which gives you the steady state gain k. This is how the steady state or static gains associated with the transfer function models are estimated. Okay. Next, we will go to the estimation of the remaining parameters of the TITO transfer function matrix models. So, the auto tuning test results in stable limit cycle outputs for any H 1 divided by H 2 is not equal to 0. That means, H 1 H 2 are not equal to 0. Then, from the loop equation, the loop dynamics gives us the characteristic equation of the form identity matrix I plus n GM bar S is equal to 0, and that in frequency domain can ultimately be expressed in the form of n times GM bar j omega CR is equal to minus I, where omega CR is the loop frequencies. So, omega CR, we assume the omega CR to be the loop frequency of both loops. So, loop 1 and loop 2 are assumed to have same signal, with same frequency, critical frequency, that is given by omega CR. Now, GM bar j omega CR is further. When you look at the block diagram, from there you can easily find out what is GM bar j omega CR. This in transfer function form will be GM bar S is equal to I plus GM GCL S inverse GM S. So, which in frequency domain is given in this form. So, this is how we get from the loop equation or the characteristic equation of the loop this analytical expression. Now, substitution of GM and GCL in the expression results in this expression. Okay. So, simply substitute for GM1, GM2, GCL1, GCL2 and get that in the general form of K I times e to the power minus j omega CR di upon 1 plus j omega CR Ti square times A1 I plus A2 I is equal to minus 1 for all I equal to 1 to 2. So, we will get two analytical expressions basically, but in general form I put the this expression upon substitution of various G's, GM and GCL, I get an expression of this form, where A1 I is equal to 4 H I upon pi A I plus K C I dash times 1 plus T D I dash upon T I dash, and A2 I is equal to K C I dash times omega CR T D I dash minus 1 upon omega CR T I dash. These are not difficult to get these expressions. It is very easy. Simply substitute the expressions for GM and GCL or GMI and GCLI in this expression, general expression, which will result in another general expression of this form, where the constants A's are given by this. Okay. So, after obtaining this, what you do, since we have got an equation in complex variables. So, that way upon simplification means equating the magnitudes of both sides of that equation. So, when you equate the magnitudes of both sides, take the magnitudes of both sides. So, what you will get basically when you take the magnitudes of both sides of this expression. So, I will get expression in the form of k I upon 1 plus omega c I t I square root is equal to, or again we have got complex numbers, say a 1 I square plus a 2 I square root is equal to 1. So, this is what you get from the magnitude, and from the phase angles you get minus omega c r d I minus 2 times tan inverse of omega c r t I is then again given by angles plus tan inverse of, no, these are constants. So, no need of tan inverse. So, angle wise they do not contribute, is equal to minus pi. So, using these two expressions, what I will get when those are solved again, when the first two are solved, then obviously one gets T I is equal to root of k I times root of a 1 I square plus a 2 I square minus 1 upon omega c r, and d I is equal to pi plus tan inverse a 2 I upon a 1 I minus 2 tan inverse omega c r t I upon omega c r. So, this is how you get the expression, final or explicit expressions for unknowns associated with the transfer function models. Now, load disturbance rejection already I have described. So, this is repeated in the matrix form H y s is equal to I plus n g s plus g c l g s inverse g s l s, and g when g c l s has got some integrator, then this in final limit s tends to 0 y s becomes 0. So, the contribution or the effects of load disturbances are nullified. Let us go to a simulation study. Consider a TITO process with transfer matrix of this form, where the denominator d e n s is given by 1 plus s times 1 plus 2 s square times 1 plus 0.5 s. For this, what initially the PID controller values are chosen as k c 1 dash is equal to 0.1, t I 1 dash is equal to 1, t d 1 dash is equal to 0, and for loop 2 the PID controllers have the values k c 2 dash is equal to 0.1, t I 2 dash is equal to 1, and t d 2 dash is equal to 0. With these two controller settings, relay experiment is conducted, and the dynamic model parameters are found to be k 1 is equal to 0.849, t 1 is equal to 1.6698, and d 1 is equal to this much. Similarly, for the second loop, the second SISO process model parameters are obtained as this. Now, another stage of relay experiment is conducted with these settings of the PID controllers. Okay. With the, then you get the final parameters for the two SISO transfer function models H, k 1 is equal to 0.849, t 1 is equal to 1.879, d 1 is equal to 0.3422, and k 2 equal to 0.678, t 2 equal to 1.7573, and d 2 equal to 0.3271. Thus, we obtain two SISO transfer function models with these parameters after two relay experimentations or two relay tests, and these are the final values and found to be representing the dynamics of the TITO process. So, what we have studied here, set of analytical expressions are presented discussed for online identification of the TITO process dynamics. So, two SISO transfer function models, transfer matrix are obtained. Now, presence of the controllers in the loops ensures that the static load disturbances do not affect the system outputs or sustained limit cycle or sustained oscillatory outputs. Now, symmetrical limit cycle outputs are obtained automatically during the symmetrical relay experiments because of the presence of the controllers during the relay experiments. Now, no effect of static load disturbances on identification result, and the analytical expression has been given and proven. Now, what are the limitations of the online identification technique? One major limitation associated with this technique is that we are using the describing function based analysis. Now, the describing function does not yield more number of inequalities as far as analysis based on describing function is concerned. Therefore, one has to assume the transfer function models, the SISO transfer function models having less number of unknowns. That is all. Thank you.